started. Hi. Good morning, everyone. We are working on optimizations. The ones that are left up to question 18 kind of fall into about 5 different categories. We're going to do some rectangular fields questions. A lot of questions about boxes, cuboids. A weird question about a poster. Another question about crossing a river. And the last 2 questions are on optimizing an oil refinery piping somewhere. So that is the basic optimization topics that we're going to be doing. I'll get a little note at the bottom. It hasn't happened yet, but it will happen. It's solving the critical number problem, right? When is the derivative 0? If it's not possible algebraically, then you can use Desmos to find a solution. For example, you might get a derivative that looks like this: 3x plus 2 times the square root of this guy, and you're trying to make it 0. You would have a really hard time, if at all possible even, to solve that algebraically. So what you would do is you just plug that into Desmos, and right, you plug the derivative into Desmos, and then you just find that guy. Right, you find out where it crosses the x-axis, and that's the guy that you're looking for. Right. So let's jump right into the first one. This is a farmer wants to take a rectangular field, looks like this. You're told that the area is 37.5 million square miles. Square feet, good grief. Square feet. Splits it into 2 like that. And we are being asked eventually to find the minimum fence. So we're being asked to find the smallest perimeter. Well, I'll call it the smallest fence length. Okay, so we know the area is 37.5 units. Find the smallest fence length. Draw a little picture. I'm going to call that distance x. So the length of this rectangle is going to be called x. This guy here is going to be called y. That's the width. We are going to find the length and the width, essentially, of a rectangle that has this area, but has the smallest total length. Okay, so let's call the optimization function L for the length of fencing that you would need. In this picture, you need 2 x's plus 1, 2, 3 y's. You're told that the area is 37.5. That the area of that rectangle is xy. So what you've really been told is xy is 37.5. And what that allows us to do is to find out what y is in terms of x. So my optimization function is 2x plus 3y. That's now going to become 2x plus 3 lots of 37.5 over x, which is 2x plus some really awkward decimal, 112.5 over x. And that's step 1 done. You get that guy. The rest of the question is pretty much the same every time. Aren't I going to differentiate this guy? And then I'm going to find the critical numbers. And one of those critical numbers is going to be the one that is the solution to the problem. So I'll now differentiate. Just respect to x. This guy gets me 2. This guy, you're going to trust me, ends up being that. Do you agree? The derivative of this is that. Are you happy about that? You need to see where it came from. Yeah, we're okay with that. So what we're going to do now then, it's basically step 2. All right, we're going to set this to 0, which means 102.5 over x squared is going to be 2. We cross multiply, 2x squared is going to be this guy. So x squared is going to be, 56.25. And that makes x plus or minus the square root of 56.25. And the square root of 56.25 is 7.5. There's a surprise. Well, one of them is positive and the other one is negative. I'm going to kill the negative one. Why is a negative x value not sensible in this question?
You can't have a negative unit of fencing.
That's it. So we know our answer. The length of this rectangle is going to be 7.5. The units are million square feet, but 7.5 is enough. As long as I stick to the units, I'll be fine, I believe. If not, the answer is that. Depends on which one of those two WebAssign is looking for. Now, to get the width of the rectangle, if they want that, yeah, they do. Won't I just take this guy here and replace x with 7.5? Let's find out what that gets me. 37.5 divided by 7.5, and I get 5. Or 5 million feet. That's one heck of a big fence. Are we comfortable with the process of using the information given to get the optimization function? And then do step 2 in this bit here. Step 3. So you find that guy, you differentiate him. Technically speaking, isn't x equals 0 also a critical number? But I won't use x equals 0 because doesn't that make the rectangle disappear? Right, and that isn't a practical solution. Okay. Your box story. Question 11. A box with a square base and an open top. Okay, so it's got a square base, so that's going to be x by x. It's got an open top. Not too bad. Yeah, I've just drawn a box with a square top, right, and an open top. A square base, I should say, and an open top, right? So, square base, within this. What do we know about this one? We are told that its volume of this box is 62,500 cubic centimeters. And we're being asked to find what the lengths of the rectangle are, right? What the length, width, and height are, what the dimensions are. Something there. Oh. And we've been asked to minimize the material used. It's an interesting phrase. The optimization function is going to be the material used, and we're going to find the smallest number. Right? Obviously, that'd be the cheapest way to do it. What do you think they mean by the material used?
Surface area?
Surface area.
Yeah, surface area. Now, be careful with this. This is an open-topped box. So if I went and said, we'll call it S for surface area, because someone used that term, I like it. Would you agree that this box only has a base? Because it's open-topped, right? There's no lid. And the base has an area of x squared. And it has 4 vertical panels as well. What's the area of these vertical panels? Of any one of them? Like this one here. What's its area?
XY.
XY. Now, since there are 4 of them and they're all the same, is it okay to write plus 4xy? Can you see where that comes from? Now, all I need to do is figure out what that y is in terms of x, and don't I have my optimization function, and I'm good to go, right? I need to find what that y is in terms of x. And the only guy in town that's going to help me is that piece of information there. And if you want to get the volume of a cuboid, it's its length times its width times its height. So that's x squared y. If you tell me its volume is 62,500, then you get that. And then you can divide both sides by x squared. Bingo. That's the guy that's going to be used here. So the surface area is going to be x squared plus 4xy. And then I'll just make it a little bit prettier. Well, that's going to be a big number, but I might as well find out what that number is. So 4 times 62,500. Oh. There you go. There is your optimization function. Not going to do the rest, but won't we find its derivative? Won't we find out when it is 0? That'll give me our critical numbers. And one of those x's is our solution. Right. Once you got that, isn't the finish derivative set to 0 typically, or undefined, but typically 0? Those critical numbers, you may get 2 or 3 of them, but one of them's the answer you're looking for. Sometimes you can kick out a critical number because it's negative and it doesn't make sense. Sometimes you kick out the critical number because it's 0 and 0 makes the shape disappear. If you have 2 numbers that still survive, then you plug them in and you figure out which one's smallest. Right. So one might give you a 40,000, the other gives you 20,000. So the one that gave you 20,000 would be it. Are we good with that box question? Let's try another box question, because there's lots of them. Question 13. A rectangular storage box without a lid is to have a volume of 10 cubic meters. Okay. It's pretty much the same as the first one, only this time the length of its base is twice its width. You see how I did the length of the base is twice its width by using x and 2x? And this box looks kind of like a box you'd have cereal in, is also open top. So it looks something like that. So far, so good. Now, it adds one more layer to the puzzle. It says here, oops, got to get this stuff out of the way. The cost of the material that you use to make it is different depending on what you've got. The cost of the base, right, this bit here. That stuff costs $20 a meter. $20 a square meter. And the side panels, they cost, so that's one of them is there. The side panels, they only cost $12 per square meter. So if it wasn't bad enough, we now have to introduce this information into our puzzle. Right? Now, we are trying to minimize the cost. So I need to create a function that is the cost of the material used in building this box. Right. What is the area of the base? In terms of x and y, what's the area of the base?
2x squared.
Agreed. Isn't this 2x and this is x? So it's 2x squared, right? But wait a minute. If it costs $20 a square meter, won't the cost be 20 2x squared? Are you happy where the 20 next to the 2x squared is coming from, right? The base is 2x squared and it costs you $20 a square foot. Now I'm going to add to that the 4 side panels. Would you agree that the side panels are x times y and 2x times y and x times y and another 2x times y? Can you see that the 4 panels are not all the same size? The bigger ones are 2xy's, and there's 2 of them. And the smaller ones are just xy, and there's 2 of them. So that gets me 4xy plus 2xy. That gets me 6xy. So 6xy is the area of the 4 panels added up. And they cost $12 a square meter. Are you happy where the 6xy came from and why it's being multiplied by 12? The vertical panels cost $12 a square meter. And if you add up the 4 side panels, that's their area. So the cost function is 40x squared plus 72xy. Now I know the volume is 10. The volume of this box is its length times its width times its height. Let's see what that looks like. 2x squared y. And we know it's 10. That means y then is 10 divided by 2x squared. That makes y 5 over x squared. So I now have...
When you're doing this,
yes.
Aren't you doing 20 times 2x? Okay, 40. That's what I was...
Are we good? 48, yeah? It's 20 times... Yeah, 20 times 2 is 40. plus 72x times this guy. And the cost function is now 40x squared plus 360 over x. That is step one done. I have a cost function, right? I have an optimization function. Right, I differentiate that, I solve it, I get a value of x, it works. I think you get two values, one's plus and one's negative. They throw out the negative one. I'm not going to use 0 because wouldn't that make the box disappear? So there's only one x left, and that's the guy you're going to use. Are we good? Now you see, they keep adding layers and layers to the puzzle. It starts off with a box, and now it's a box where the bottom costs a certain amount, but the vertical bits, panels cost different amount. And we got it. Next, pellets. Let's do a poster. There's only one of these. This is question 15. I am only going to create the optimization function again. This is essentially a copy of the same picture that they have. There's a picture with a frame around it. The frame, even if it doesn't look it, is 12 top and bottom. And you know, though it doesn't look like it, you pretend that I'm good at drawing, and it's 8 side by side. The area of this picture, right, which I am going to call that distance x and this distance y. We are told that the area of that picture is 1536. And what's the unit? Square centimeters. And we are being asked to find, so this is our optimization, right? The smallest area for the poster. That's a picture. The poster is the whole thing, okay? So that shaded guy is a picture of your dog, and this is the, you know, the big poster thing that goes around it. So what do I know? Let's take the area first. I decided to call this x times y, so the area is xy, and we're told that that's 1536. So I now know what y is going to be. Kind of doing this slightly out of order. That's that guy. Now I'm going to find a formula for the area of this poster. If I want to know the area, don't I need to know these two dimensions? Great. Now, if the distance from here to here is called x, what's this distance in terms of x? From here to here, right? From here to here is x. What's this distance?
X plus 16.
You all agree on that? X plus an 8 and another 8. And won't this vertical distance then be y plus 12 and another 12? Are you happy about the y plus 24? So far, so good. So won't the area be length times width? And our optimization function then is x plus 16, and then replace the y by this ugly fraction, plus 24. Are you happy about the y gets replaced by 1536 over x? And don't we now have an optimization function in X's? Good luck with that one, because you're going to have to differentiate it, and it's not pretty. There are two different approaches. Couldn't I leave it as is and do a product rule? What would be the other approach to find this derivative? We could just leave it the way it's written and do a product rule on it. That's one approach. What's the other approach?
Could you FOIL it and then differentiate it?
Yeah, me personally, I would seriously think about foiling this thing out. It's still going to be as ugly as heck, right? No matter which way you do it, it's not going to be pretty. But this might be a candidate for Desmos. Can you imagine when you're finished with its derivative, it might just be so ugly that it might not be able to solve it equals 0 very easily. And that's as far as I'll go with 15. And now we are doing crossing a river. Very classic question, crossing the river. There is a heck of a lot of stuff in this story. They do give you a picture, which is something. There's a guy at A, and this man is in a boat, because this is a river, right? This here is a river. There we go, a river. And he is trying to get from this side of the river at A to some point on the, let's say, a man launches a boat to A on a bank of river, 4 kilometers wide. Okay, so that distance from there to there is 4 kilometers. And he wants to reach a point B. He wants to eventually get here. He starts here, he wants to get here. Now, what's the problem? Well, the point B is what, 4 kilometers on the opposite dynamic. So if I draw a little invisible dotted line, this distance from here to here also happens to be 4 kilometers, but it might not be. It might be 3 and 6 the next time. Now, he has choices about how he's going to get to B. He could row straight across, right, perpendicular to the bank, to a point C, and then he could walk from C to B. Or he could just go and row all the way to B. Or, now it's getting messy, there is one third alternative. He could decide to row to some other point here, we'll call it D, and then walk the rest. So he's got 3 choices. Does he just row to C and then walk to B? Does he just row straight to B? Or does some kind of compromise in the middle where he rows a little bit to the south, but not all the way to B, and then he walks the rest? So how are we going to make this question even more messier than it already is? He rows at one speed, but he walks at a different speed. So you are going to be told that the speed that he rows, so when he's in the water, this is the speed he's going to go at, is 6 kilometers per hour. And when he reaches land, walk or run, I don't care what we call it, we'll call it run. And when he does that, his speed is 8 kilometers per hour. So far, so good. Now, what we want to do here is minimize the time. In other words, he wants to do it in the quickest time. It's going to make sense. So somehow we have got to do an optimization function that solves this puzzle. Well, the one that really needs a formula is the A to D DEB one. Because can't the other two just be calculated as numbers? So let's get them out of the way. Let's suppose he does A to C, then he goes C to B. Let's figure out what the time would be for that journey. Right, A to C is 4 kilometers, and he rows at 6 kilometers, so that's 4/6. C to B is 4 kilometers. He runs at that speed. That ends up being, okay, let's see how long that is. 4 divided by 6 plus 4 divided by 8, and turn it into a nice fraction. And that answer ends up being 7/6 of an hour. Okay, so his other choice is A to B directly, right? Well, to do that, don't I need to know the distance from A to B divided by his speed? And if you look at this, isn't this a 4x4 rectangle? A rectangle triangle. Can you see the 4x4? So that distance is the square root of 16 add 16. It's the square root of 32 divided by 6. And the square root of 32 divided by 6 ends up being 0.942 hours. So that one's no good. Would you agree this is quicker? Because that's 1.16. And now the killer. The time it takes to go from A to D plus B to D. That's the optimization function that is the challenge here. So I'm going to draw another little guy because I'm running short of space here. Here's A, here's C, here's D, here's B. That distance is 4. This distance is 4. I am going to call the distance from C to D X. So when I tell you X is 3, that means he lands 3 kilometers south of C, for instance, right? So far, so good. Now, if I want to find the time it takes to do the journey A to D, then I need to know what the distance from A to D is divided by his speed, which is 6. What is the distance from A to D in terms of X? Can you see in my picture, if I just isolate what we need to look for? What is the distance from A to D in terms of X? Think Pythagoras. What's the distance from A to D?
4 squared plus x squared equals
Inside a square root. Great. Divided by 6. So that's going to be the square root of x squared plus 16 divided by 6. Okay. So over here, the square root of x squared plus 16, all divided by 6. Okay. What is the distance from B to D in terms of x?
Four minus x.
You all happy about that? Where it came from, 4 minus x? And so that's going to be what, 4 minus x over 8? So 4 minus x over 8. And there is t. We have found the optimization function. It's this ugly thing. Which I can tidy up, but not actually that much. Can you imagine when you finish differentiating this function, it will be really weird looking, but won't you be able to then hopefully find when it is 0? If it's algebraically really ugly, which I strongly suspect it is, can't you just plug it into Desmos and find out where it crosses the x-axis? And according to what I've got here, it says that it's an unexpected solution. I have no idea what unexpected solution means. I guess we'll find out when you finish it. I don't know what unexpected is. I think I've expected everything. I mean, couldn't it just go straight across and walk down? That might be the answer. Couldn't it just be go diagonally across? That might be the answer. If I find out what x is, right, won't I be able to find the time it takes? And one of those 3 numbers is going to be smaller than the other 2. So I don't know how I'm going to be surprised. I don't know. I really don't know what they're getting. I guess it. You'll tell me tomorrow. Right. We've got one last group of questions to deal with. And that is oil refinery question. And there's 2 of them. And I don't really know which one. Right, let's do 18. Our last question. An oil refinery, this one doesn't have a picture, right? An oil refinery is located on the north bank of a straight river that is 2 kilometers wide. So, okay, so here is the river. And that river is 2 kilometers wide. And I'm going to put that as my oil refinery, and I'm going to call it O for oil refinery. A pipeline is to be constructed from the refinery to storage tanks located on the south bank of the river, 8 kilometers east of the refinery. So if you draw a little invisible dotted line to here, and then you go east to here, you're getting a guy called the refinery. And that distance is 8 kilometers. You see what I'm basically doing is just reading the story and drawing a picture as the story moves on, right? Now, what else do we know? Oh, they tell us some cost things. The cost on land to build a pipe is 400,000 a kilometer. So $400,000 every kilometer. And if you do it in the river, the cost of the pipe on the river is twice as much. So I guess it's more expensive to do it under a river than it is on land. Makes sense. And we are being asked to minimize the cost. So I guess it's up to us to make this decision. By the way, now that I see this question, it's actually a version of the river question. couldn't you go straight north-south and then straight sideways? Couldn't that be the cheapest way of doing it? Couldn't you go all on the river? And then you have to pick some point that's a bit of A and a bit of B, right? A bit of one, a bit of the other. So that means there are three different costs. I'm going to have to put my own letters in. So that's going to be A, and I'm going to call this guy B, right? That's already called R. And I'm going to look at three situations in. Two of them do not involve calculus. Couldn't I just go O to A and then A to R? So that would be directly to the other side and then straight the whole thing. Now that would be 2 kilometers costing 800,000 plus a straight 8 kilometers costing 400,000. And that would be 1,600,000 plus another 3,200,000. And that would give me a grand total of 4,800,000. Are you comfortable about how I calculated the cost of that solution? 2 kilometers plus 8. 2 kilometers at 800,000 a kilometer, another 8 kilometers costing that per kilometer. So that's my first situation, right? My second situation, right, would be just doing OR. Right, straight line from O straight to the refinery. Now, in that case, it is going to cost me 800,000 for every kilometer, but I now need to know what the distance OR is. Well, there's a lot of little pictures going on here, but this distance is 2, and this distance is 8, and OR is that guy. Would you agree that OR then is just Pythagoras again? And it's, what's it going to be? 64, 68. So it's the square root of 68 times that. Let's see what that looks like in money. Square root of 68 multiplied by 800,000. That's going to cost you, well, forget about the pennies, 6596969. That's going to cost you 6 million. Okay, so you don't do it that way. Would you agree it's cheaper going straight and then across? So that isn't my possibility. Now the killer. I want to find the cost if you do O to B and then B to A. Now O to B is on the river, right? So that's going to be 800,000 times the distance from O to B, and B to R is on the land, so that's going to be 400,000 times the distance B to R. Right, let's figure out how to get this distance here. So I'm going to, I guess I'll do it under here. Here's the river again. Here's O. Here's B. Here's R. That distance is 2. This distance is 8. And I'm going to call that distance X. So OB, can you see Pythagoras again? Square root of x squared plus 2 squared. What's the distance BR in terms of x? What's the distance from B to R in terms of x?
8 minus x.
Right. It is very, very similar, isn't it, to the river crossing one? I know that the story is different, but the math is looking very similar. In this case, it's going to be 400,000, 8 take away x. So here is our cost function. That's step one done. A few minutes, I'll try and take it a little bit further. Step two, differentiate it. Okay, that guy is actually, if I bother multiplying it out and then differentiating it, can you trust me that you end up with negative 400,000? You just trust me on that, that's what you get. Now this ugly guy, I would have to call x squared plus 4 to the half. So what you're going to get is 400,000. This guy on the bottom times a 2x. And I didn't leave enough room here, so the derivative is going to be 800,000 x over the square root of x squared plus 4 minus 400,000. You can just trust me that that's a derivative. You can check it later. Now, I want to find out when this guy is 0. Would you agree that is one ugly looking equation to solve? So let's do it on Desmos. So I've been saying, look, when they get really ugly, you kind of need to, improvise. So here we go. I'm going to call this function y equals, just to make it easy to type. And it's fraction. Well, I don't need to worry about that. I'll do it anyway. 800,000. Yeah, divided by, that will make the fraction. The square root, which I do need. And x squared plus 4 take away 400. And, well, I know you can't see the curve, but can you at least see where it crosses the x-axis? Can you see that the value of x then is 1.155? I don't need to worry about other ones. Maybe there's another one at x equals negative 10. See if there was, won't I ignore it anyway? And there might be another one at x equals 22 or some weird number like that. Won't I ignore that one as well? Just in the context of the story. So I know that's the right answer. Do you see how you can find it, even if it's not pretty? If you want to see the thing, I guess I could try shrinking to the point where, oh God. Well, no, I'm not going to be able to shrink it. Can you see how big these numbers are? I'd be here all day trying to get the vertical scale to show you. Let's do it the opposite way. Let's just zoom in. Yeah. Isn't that the only guy I'm interested in? Even if I can't see the graph, I can see where it cuts the x-axis. And so we have our solution. Well, it might be our solution. I just had a nasty thought. Didn't this one cost 4,800,000? I don't know if you can see this, so let me kick it in. Remember the one here, this one just going straight was 6 million. I kicked that one out. See the one that went this way and that way, didn't it end up being 4.8 million? Shouldn't I take my cost function and use that number? So I should be plugging into here, that guy. Now I'm making up two scenarios. I plug it in and the answer ends up being 4,100,000. Then doesn't that make that the cheapest? Right. Suppose I plug this in and it ends up being 4,900,000. Doesn't it make this guy over here the cheapest? So don't I need to check my solution against the ones, one of the other scenarios that could be the case? And I have overshot your time. I apologize, but I felt I needed to finish that question to the end because it is that's a pretty cool question. Okay, say hi and bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you.
Okay, bye-bye, guys.
You
Yeah,
have
look-
office hours today, right?
I will definitely be here for my officer. I might be working up to and including it, but whenever you come, I will stop working because I'm
Okay,
assuming you've got some questions for me.
I do. I'll see you there. Thank you.
I'll see you there. You know where it is? It's the same link.